Okay. We're going to finish off today with the end of the linear algebra slides, and then we're going to start with analytic geometry. There's one kind of last bit of linear algebra that I thought we'd leave for today, and that's the ideas of image and kernel, and then what's called the rank nullity theorem. And this theorem kind of ties together all that we've spoken about already, things like null space and kind of projections and change of bases. So it's important to know. And then there is a proof of it online that I'll just walk through very quickly, but it's mainly for you guys to have a look at. So the definition of the kernel is this first one here. Let me grab my pen. If that happens and I don't notice, please stop me, because it means that it's not going to be on the recording. Okay, so the definition of a kernel is also the definition of the null space. So we know kind of what the null space is. We spoke about it. When I apply a mapping to some kind of vector space, it's the parts of a vector space that gets left behind. Okay, if I have my vector space, which is a box, and I'm applying a mapping that has a null space, it's the same as squashing the box. Okay, there are parts of it, there are directions in that box that get flattened. All right, and that will correspond to some some vector pointing somewhere in that 3D space that now gets lost. So it doesn't have to be the case of I have my kind of cube and I'm squashing a vector in one of the cardinal directions. That's obviously one way to do it. It can be the fact that there's a vector pointing at the top right corner and I'm squashing along that way. Now we have this flat box where the two corners have been touched together. So geometrically, that's the intuition though. There's some direction in that vector space that is not being preserved when I apply the mapping. Okay, that direction, wherever that vector is pointing, is the null space. Okay, so in 2 dimensions, it'll look like this. We start with our, we can't form the sides. We start like this, okay, and then I'm applying some projection that might be squishing along that direction there, right? In that case, the null space is this vector here, this green vector. Any vector that sits along that line will get forgotten when I apply the mapping to a new space, which is, let's say, this line. Okay, that mapping will happen from this yellow vector that you can't really see, or this yellow matrix that you can't really see. That'll be what applies this mapping onto the blue line. Okay, so you can see that what gets lost is always orthogonal then to what remains. So it's always going to be the green line, the null space, is going to be orthogonal. I'm struggling. It's always going to be orthogonal to this blue line. Like that. That's the idea of the kernel, and we will come to, again, a little bit more of a sophisticated idea of it now. That's the intuition, okay? It's just what information I can no longer represent after my mapping. And you can state that formally by saying that if I have this mapping over here, then my kernel is all vectors such that when I apply my mapping to it, I get the 0 vector in the new space, okay? Obviously, it's not a 0 vector in the old space. There is some kind of direction in this room that vector could point to, and then only in my new space have I lost that information, have I collapsed it down. Okay, based on what we said last week, and maybe this diagram up at the top here, does anyone want to hazard a guess? If A has a null space, is it invertible? Someone say something. It is invertible. Okay, let's think it through. So if I start with a square and I am mapping onto this line here, and it's this blue mapping there onto the line. If I asked you to undo this mapping, right? If I have this dot here, let's pick a different color. If I have this orange point over there in the middle, that doesn't look different, and it gets mapped there, but I also have a point over there that also gets mapped here, right? Because I'm just squishing everything down along this axis here. And I asked you, where does this orange dot go to when I'm doing the inverse mapping? Where would you say it goes to? It goes to the right one. So you mean there. Why not the other one? Okay, let's say it again. Okay, so I have this space on the left. It's a square. I'm applying some blue mapping, which is a matrix A, and I know that I land up on this green line. Okay, I'm telling you that both of these orange dots there on the left get mapped to the orange dot get mapped to this orange dot on the green line, okay? So they're both going there and there in this direction. So I then do the inverse problem, okay? That's fine, we know how to do that. I do the inverse problem, I give you the dot on the green line and I say, give me its place in the red box. Well, maybe, yeah?
So I was going to ask, when you have, like, let's say, just like real numbers,
Yeah.
like the 0, obviously, like the...
Yeah.
Would that also be considered a null space?
Yes.
So
we're coming to that now, yeah. Yeah, good question. So the point is, and I think you're touching on the correct answer, but the conclusion then is incorrect. The answer is you can't undo it because I don't know which of these two dots I land up on. So as much as it could be, you know, like it can't be either, we've lost that information. I can't now retrieve it on the way out and tell you which of the two dots I map back onto. Okay, this has a null space. Whatever lies along this line connecting the two dots over there is the null space of the blue mapping itself. It's what information I cannot retrieve after I've applied the mapping. That line, any point that lies on that line is called the kernel or the null space. Null space, it gets mapped to 0. Mapped to 0 means it's forgotten. Okay? Does that make a little bit more sense? Yeah. It is? Yeah.
The inverse mapping will just produce that there.
So the math notation is a bit subtle. So let's get the pen out. So what this is trying to say is it's, yes, the set of points such that if I give you 0 on the right-hand side, it will map out to the original side. But I don't think that's, I think this is a stupid definition because there's no such thing as the inverse of that mapping. This is like a very general notion of it. In matrix multiplication and in linear algebra, you cannot do this inversion, right? That won't happen. It's the determinant 0. You see what I'm saying? So that's admittedly why I didn't focus on this one. I focused on this idea. This makes much more sense because this is the forward mapping. It's saying it's all vectors in my original space V, such that is the two dots. That's how you like read it. So it's vectors in my original vector space, capital V, such that when I apply the mapping phi to it, I get the 0 vector in W. Yeah.
Would that inverse notation work if you only have one mapping from the 0 V to the 0 W?
Yes, but then you wouldn't have a kernel. Then you got what Luca just said, where the kernel then is just the 0 elements. That's the only way to then keep this consistent, where if I take an element of V and map it onto 0, okay, map onto the 0 and W, the only vector that satisfies what you just said, such that I can retrieve it, is the vector that starts at 0 in the V space. Then I know, okay, I can map out from 0 in W back to 0 in V. Good? Okay, then the second definition that matters is what's called the image of the mapping, so that's phi. And so in that case, that is all vectors in W, so vectors in the new space, such that there exists a vector in the original space and it got mapped to W. All right? So if I pick any vector, that's what that means. So any vector in the original vector space, and I apply the mapping to it, I get a new vector W. It is that set of new vectors. Okay. So to continue our picture that we were drawing, I take that, I map it onto a green line. The image is the green line. Okay. All vectors that sit along the green line, so along this direction now, going that way, is my image. Okay? And so if we put this together, I have my green line pointing that way, my image. I told you that on the green line over here was my kernel, right? So the second one on the left is what gets forgotten in the original vector space. And then the line on the right is what is preserved on the new space, okay? If I add up the dimensions of those two spaces, the dimensions of the two green lines, in this case, there are 2, right? Does everyone agree with me on that? Okay. there are two dimensions. There's the one in the new space and then the kernel in the old space. That will always equal the original dimension of the box. So I had a 2D square. One dimension was forgotten. One dimension was preserved. It has to then equal the original space I was speaking about. Okay? And that's what I was talking about last week with the difference between vectors being embedded in a space and the actual dimensions that they occupy. Okay? If I tell you that I'm looking at the vector space A, B, C, okay, and all vectors that we can construct from that, so the span of A, B, C, excuse the handwriting, this is a one-dimensional line, right, pointing in some direction of A, B, C, but it's embedded in 3 dimensions. It's as if again, let's use the corner of the room as my origin. It's literally just one thing pointing that way. I can't describe any point in this room other than what's lying along my hand. I can't tell you about going that way off of it or going upwards off of it. It's only towards the other top corner of the room, okay? That is then a 1D vector space embedded in 3 dimensions. The embedding space is the box, okay? And then after I apply the mapping is the new image of that mapping. That's actually how much space it preserves. So the fact that these 2 green arrows, these 2 green spaces equal the dimension of the original red square is called the kernel nullity theorem, okay? It's also got I think it's what, the fundamental theorem of linear algebra or something. It's like the big deal of this whole field. If you understand those 2 concepts, you pretty much have, you know, a bunch of linear algebra down, okay? Lower dimensional subspaces are embedded in higher dimensions. Once I apply a mapping, some information gets lost. What gets lost is my kernel. What is preserved in my new space is my image. Yeah.
How do you know that's necessarily, like, I guess, squash? Like, what if you have a linear transform that just turns the box into another box?
Then it's invertible. Then my kernel is 0.
Then you don't have a kernel. You don't have an image.
You do have a kernel. It's a 0-dimensional kernel with 1 element, 0. Yeah. So just also don't forget, sorry, that's a subtle thing. If a set has 1 element in it, it has no dimensionality. We call that dimension 0, but it has 1 element. There is a difference between an empty set and the 0-dimensional set of just the null value. And if you remember, ignore that last point. That was just a terminology that I brought up that I can't now not define. If you remember when we were going through the system of linear equations, right, what did we get? We got a particular solution. Then we looked for the general solutions after that. When we were looking for the general solutions, we were looking for AX equal 0. We were looking for the null space of A. All right. What information couldn't be preserved about X when I was mapping it with A? All right.
So I just want to clarify. If it does get mapped to like another 2D space, then it has the 0 kernel but no image.
Yeah, the kernel then is just your kernel is then that particular solution. It was when you were doing the system of linear equations, that's when we say that X is equal to 0, right? It's the trivial solution. That's when you have the only element in your kernel is the 0 vector. There is an image. The image is then your 2D new mapping space.
Okay.
Yeah, so I mean this would still hold if we took a square and mapped it onto another square, if you can draw properly, I guess. Yeah. What's up, mate? Yeah.
Yeah, I wanted to ask. So then, does that mean that if a map is inverted, then kernel has dimensions?
Correct. With 1 element in it, the 0 vector, right? Correct. Is this kind of starting to gel? Yeah.
You said that the kernel is what's lost from the mapping of A, the matrix A.
When I apply A to a space, so again, in the system of equations, AX equals 0. X is the vector space I'm applying A to. Okay, so then what information about X can I not keep? What will happen if you're in a situation where you are losing rank, where you have a kernel like that? That's when you get into a contradiction in your system of linear equations, right? You might be embedded in 3D. You might be embedded in 3D, but you have A, B, C, D, E, F, and you're trying to map this onto another 2 variables, X, Y. No, let's not go X, Y. Let's go something better. You're trying to map this onto alpha, beta, right? If you were doing that, then you would get to a case where you might end up with C and F not being 0, but now it's as if there's you might get like a 0 element at the bottom or something. I drew that way. That's a bad example. But my point is that if you then have a kernel, if you have a non-negative, a non-empty kernel or a dimension greater than 0 kernel, there is either wiggle room or you might run into a contradiction, which is the case that I have low rank on the left-hand side and I'm trying to project into a high rank on the right-hand side. Okay, so if let's say I was trying to find a way to map off the square into a cube or something like that. I'm going to draw the cube. If I was trying to go from a square into a cube and I needed to optimize that, you're not going to be able to do that properly. Or you might run into a situation where there's just no conceivable configuration coming from the lower rank system on the left to a higher rank system on the right. So that's why you want to look at the number of rows versus number of columns, essentially, of your space. Okay. Is everyone getting the big picture of this? Again, a lot of what I've said now about zero-dimensional kernels and stuff, like that's not super important. Are you appreciating the fact that when I apply a mapping, something gets lost and something's remembered in my new space? We're good. And the amount of information in total must equal the amount of information I started with. Okay. Let's move forward. So consider a linear mapping where V and W are vector spaces. It then also holds that the 0 element of my original space will always map to the 0 element of my new space. Therefore, you can't really see it. 0 in V is an element of the kernel of phi. Okay, so again, that was the point. There's always going to be at least one element in your kernel. Okay, and the null space or kernel of a linear mapping is never empty. There will always be 0. Then the image is always a subspace of W. Okay, and the kernel is always a subspace of V, like we're speaking about. It's always the kernel is always talking about the original space, and the image is always what you map into in a new space. Okay, and then lastly, phi is if phi is injective, if and only if the kernel is just the set of zeros. Okay, injective, it can be inverted. All right, and so let's consider a mapping, M by M matrix and a linear mapping phi. So this phi is defined as I take an element x and then I map it onto the new A by X space. All right, that's the definition of this function. For A, where the AIs are the columns of A, you can obtain the fact that the image of this mapping is just the set of vectors AX such that X comes from my original space. All right, so it's just the definition mapping here, matching that. But now I've told you that phi is just a linear mapping, which in linear algebra is obviously what we care about. Okay, and importantly, what you will notice is that it is a linear combination of my A's. All right, if I'm going A times X, all right, we go back to the kind of trick that I always like to use when doing matrix multiplication. You know that you're going to have the A1 vector in the first element, A2 in the second, A3 in the third, and so on. And then you're multiplying that by another vector, which is x1, x2, x3. Okay, and so then when you write that out, you get it as a sum of each of these vectors on the left multiplied or scaled by their x value on the right. Okay, it is a linear combination of the A's. And so that gives us our image. Whatever I can reach via a linear combination of A is my image, and so it's the span of the columns of A. All right, that's important. You will also hear people talk about the column space of a mapping. Okay, again, so because I'm making a linear combination of my A's, I can only construct data from those columns. All right, so let's consider that mapping again. Then the rank of A is the dimension of my image. Okay, so in the other case, when I got my image as being a single line, what's the dimension of that single line? It's 1. Again, it might be embedded in something higher, but it's just a straight line. Maybe it's constructed from a single vector, might have 2 or 3 elements, whatever. So then that is the dimension of it. That's my image. All right, so the amount of degrees of variation I have in my new space, that's the rank of my image. Okay, that's the dimension of my image. and that is the rank of A. All right, the number of dimensions I can represent via the columns of A. Okay, and again, that's just because it's being made out of a linear combination of A. I can't represent 3D space if I have 2 columns in A. Okay, the space I represent might be embedded in 3D, but the amount of degrees of variation I have with 2 columns is 2 dimensions, rank 2 mapping. Okay, and then the kernel or null space is the general solution to the homogeneous system of linear equations AX is equal to 0. So we went through that. This is the rank nullity theorem. I need to clean the slide. This is from an old copy of these slides. So I'm not going to go through the proof as it's written at the bottom there. I have a new one that I'm going to switch to now, and that you guys can read through and should know. So the rank nullity theorem is exactly what I've just been saying for the last, 10 minutes, which is that if I have 2 vector spaces, V and W, and a linear mapping between them, right? The dimension of V is how many degrees of freedom I have in my initial space. The dimensions of my image is how many degrees of freedom I have in my new space, okay? It was the rank of A, it's the number of columns in A. That was this. You can check the previous slide. That's what they were saying. Lastly, the dimension of my kernel is the amount of information, the dimensions I forget from my original space. And so we know that they must be equal. The 2 green vectors, when I was looking at the original 2D red square, there were 2 one-dimensional lines. 1 dimension in the kernel space on the left, 1 dimension in my new space on the right must be equal to the square. Okay, to draw that out, it was 1 dimension in my kernel space, 1 dimension in my new space. I was doing a mapping that must be equal to the size of the original square, 2. But this is going to hold in general, right? No matter how many dimensions you want to apply this to. If it's 4 dimensions and I map into 3 dimensions, I must lose 1 dimension. The dimension of my kernel is now 1. If I start in 4 dimensions and I map onto a line, okay, if I map onto a 1D space, then I'm losing 3 degrees of freedom. Okay, so the dimension of my kernel is 3. Is that making sense? If you're getting lost now, you do need to speak up. I'd rather irritate the people who think I'm going slowly. If this isn't setting in, ask Yep. Yeah. So I'm starting with data sitting in a cube. All right, that cube in reality is like going out in all directions. There is some direction of information that my mapping will lose. What that means is that when I apply my mapping to it, it gets set to 0. Okay, such that whatever after that, like if I'm going to then go, B plus that, AX, it just keeps B the same. There's no change, it applies no change to a vector in that direction. Okay, that is the X values in my original space that get mapped to 0 by A is called my kernel. It's the amount of information that gets lost when I apply A. Okay. On the flip side, the amount of information that is kept, all right, the dimension of my image, that's on the other side, that's the amount of information I can still keep. The amount of information I keep and the amount of information I lose must be equal to the amount of information I start with. That's essentially what this theorem is saying. Does that help you? Sweet. Okay, so the following important results follow directly from the rank nullity theorem. The dimension of your image must always be less. If it's less than the original space's dimension, then there is a non-trivial kernel. If they are equal, then it means your mapping is invertible and your null space is just the 0 vector. Okay. If your mapping is the transformation matrix of phi with respect to an ordered basis, and your dimension of your image is less than the original space, then the system of linear equations has infinitely many solutions. If it has a kernel, it means that there is at least a line or more dimensions. There are some degrees of freedom I can move around that will always get mapped to 0 when I apply my mapping. So I have general solutions. I can just pick arbitrarily in the space because I know it's going to get forgotten by the mapping anyway. All right? That's what, when we're solving a system of linear equations, that's what we're doing with a general solution. We're just moving around the space that gets forgotten. but you have to still describe it. You have to say that I could, instead of selling a chair, I could break it and just sell the wood and the steel. That's what that tells us. When we actually formulate linear algebra problems properly, the kernel will take on the relationship of that exchange. I could exchange chair for wood and steel is the same as saying if that information gets mapped to 0, it's equivalent in my system. Okay, it's the same as me saying your box got squashed. Okay.
So if you have like an invertible matrix, does that mean it only has one particular solution?
Correct. Particular solution and the general solution are the same. Okay. If the dimension of my new space and if the dimension of my original space and my new space are the same, then the following three-way equivalence holds. The mapping is injective, it is surjective, and as a result, it is bijective. In other words, you can invert it. Okay. I can never remember which one's which about injective and surjective, so I'm not going to hazard it. But it means that every element on my right-hand side came from an element on my left. It means that every element on my left gets mapped to an element on my right. For both of those two things to be true, it has to be invertible. Okay, I apologize for my messy slides. I will clean that and then re-put it up at some point. But good news is we do have a proper proof. Okay, my point of doing this is not to scare anyone. One thing worth mentioning for this course is I do not ask unseen proofs, but I do ask proofs. So in your tutorials, particularly for some of the later chapters, you'll realize that there are one or two proofs. If it's in your tutorial, it might come up. If it's not in your tutorial, it won't. This is also considered seen, so I might ask you rank nullity theorem, so just make sure you know it. But my point is you don't have to, everyone's taking notes now. Yeah, that's good shit. My point is you don't have to know unseen proofs. I'm not here to play those games. I know that in real life, mathematicians sit and think for 2 weeks before they do a proof. I'm not going to ask you to do something on site. That's not fair, in my opinion anyway. So, but this is seen, and so best be ready. Okay, so this is now going to be, why I think this is a useful exercise for us to do is because I think I explain things again geometrically, visually. I think for me it's helpful. I hope for you guys it's helpful. But I think seeing the mathematical, analytical kind of correspondence to that helps. Okay, I think that then it kind of ties it in, bring all of it together. You can realize that what I'm doing on paper actually just has a bearing in my intuition as well. So we're gonna give that a go. So to start off with, let's just restate our properties. So the rank nullity theorem states that for two vector spaces V and W and a linear mapping between them, it holds that the dimension of your kernel plus the dimension of your image must be equal to the dimension of your original vector space. Okay, this can be shown as follows. All right, so let B be a basis for the original vector space. All right, that's this first step here. All right? Yes.
Is this going to be provided?
It's on Moodle already. Yeah. You guys are all scratching out the notes now. Yeah, it's on Moodle. So let B be a basis for the n-dimensional vector space V. So we're just teeing up our problem, all right? Just making some general definitions we think will help, and we know that the dimension of V is going to be something we're going to have to work with. Without loss of generality, we're going to assume that the first m vectors of this basis are in the kernel of a mapping phi. And for ease, let's switch notation and just call them Ki. All right, I'm just switching away from my V's. And I'm going to just call the first m of them Ki or K1 through Km. All right, the other indices stay the same. So then I go back to my V's, and it's m plus 1 up to n because we started with n dimensions there. Comfy so far. Okay, I just partitioned a whole bunch of my basis, and I said that's in the null space. Yeah. So inside of this B basis, right, there's all V1 through Vn. What that includes then is just V1 up to Vm, then Vm plus 1 up to Vn. I'll close the door now. Okay, I'm just going to take these V's, and I'm going to call them K. K1 up to Km. All right? I'm just changing the name of them just so it's easy for us to keep them separate. All right, thanks for that, Matt. So this is what we're left with. This is our basis of the V space. Okay, we are left firstly to prove that in this general setup, the image of our mapping is just the span of the new set of vectors, of the set of vectors that are not in my kernel, right? That's what we want to prove. That's going to give us a step towards proving the rank nullity theorem, and that's where we're going to start. If this doesn't make sense now, that's fine, because that's where we're going. That's actually the proof playing out, okay? So it'll make sense by the end of it. In other words, any element of our image can be written as a linear combination of Vm plus 1 through Vn after they've been mapped. Okay? So often in our proof strategies and when we do proofs in practice, what we do is we make some statement like that. We don't actually know it's true. We think that if that, usually if you understand, and again, you think about it for 2 weeks, you'll come to a conclusion that that might have a good property, and you'll write that down, and then you'll try to prove it, or you'll try to contradict it somehow. That's kind of the game you're playing. So we just wrote that down and said, maybe that matters. Okay? So since B is a basis of V, we can write any X element, any X vector from our original space V as a linear combination of our basis vectors. So some set of lambda I times our K set, and some set of mu I times our small set. Sorry, that should be small v. I'll fix that. That's small v. Okay? As a result, for this vector in my original space V, if I apply my mapping to it, that's the same as me applying my mapping to that linear combination. All right? All I did was substitute in the definition of X down there. Okay? Now we use one of our properties from last week. We know that linear mappings are distributive. Is someone all right? Do you want some water? Is someone coughing? Oh, no. So we know that a mapping is distributive. In other words, we can pull out scalar multiplications. That's what the first thing we're going to do is we're going to pull out the scalars. Okay? And on top of that, I'm going to distribute it over the summation. So now phi is sitting on the inside, and then we have a linear combination of our phi of the ki's and phi of the vi's. Okay? What you'll notice is that these, by definition, by our original assumption up top here, right? The second line, those are our kernels. That's our kernel space. We know that that maps to 0. And so I'm just going to substitute in 0 there. Okay? What we're left with is the statement that after applying our mapping to X, it can be written as a linear combination of the mapping of our basis vectors that aren't in the kernel. Okay? And I wrote there, since Ki is in the kernel, just becomes 0. But this is just the definition of the span. This says that I can write phi x for any x as a linear combination of phi vi's, where the vi's are my basis vectors. In other words, it is spanned by the phi v vectors. Are we all comfy so far? Is there like steps making sense? Okay. So this proves that my image is spanned by the original basis being transformed into the new space that wasn't in my kernel. In other words, it's spanned by what isn't forgotten. That's all that's saying. That's all we proved. My new space is literally the set of stuff that I don't forget when I apply my mapping. Nothing smarter or more sophisticated than that. What we need to say now, though, because we care about the dimensionality of my new space, I need to show that this is also a minimal set. I can't just come along and say, my new space has dimension n minus m plus 1, right? Because what happens if those vectors were not linearly separable or whatever, Maybe they are themselves kind of overlapping and stuff. And you can see where we're going. It's already starting to get slightly contrived because I already told you that they're a basis set up top here. Okay? But maybe they're not a basis in my new space. All we knew is that they were part of the basis for my original V space. So now I just need to show that it's a minimal set in my new space as well. In other words, it was a part of my basis for my original space. It is the entire basis for my new space because everything that else would have been forgotten. Okay? Now I'm going to come through and I'm going to show it's minimal. How do we show that a set of vectors is minimal? Well, we solve for its kernel. We solve for where it gets mapped to 0. All right? Is there a configuration of these vectors, sorry, phi b, is there a configuration of those vectors that gets mapped to 0? In other words, is there some linear combination that I can construct another vector from? All right? So that's where we're going to start. That's what we need to prove. All right? And so all I'm going to do now is I'm going to just run the distributive property in reverse again, and I'm going to pull it outside of the mu and the summation. And I'm saying that, well, this space that is remaining that defines my image, if I look at it again in terms of its original starting point, it means that this set of vectors here must get mapped to 0. Right? For that to be true, for there to be a linear combination of these vectors such that they're not linearly independent, if these vectors were not going to be linearly independent, then it means that they had to be in a space, in our original space, such that they get mapped to 0 in our new space. All right? Sorry, I said that a little bit badly at the end there. But in other words, what this ultimately means is that these vectors constructed as a linear combination of our VIs must be in the kernel. But that's ridiculous because I told you in the beginning they're not. We showed that they're not in the kernel already because the kernel was defined as all the other basis vectors already. In other words, these two must be equal, okay? So the linear combination of my V vectors and the linear combination of my K vectors must match, or in other words, for any vector in this set here, I must be able to write it as a linear combination of my kernel basis, which I told you in the beginning is just the K vectors. Okay? And there must just be some set of lambdas such that this holds. Okay? But for B to form a basis of my original set, those had to be orthogonal. Okay? They can't have this property because what this means is then if that was going to be true, I would have been able to write one of my basis vectors as a linear combination of my others. That contradicts the assumption that it's a basis. And so the only solution to this problem that exists is to just set my mu's to 0. Mu's and lambdas to 0. Okay? The trivial solution. Okay? As a result, they're linearly independent. I'll go through it now. Let me just finish the proof so we can see where we're going with this. I think looping back over fully will help. So what that means, because the only solution to that system of linear equations was the zeros in the mu, that means they're linearly independent. And so together with the fact that they are spanning, they're now a minimal spanning, they're a spanning linearly independent set, so they're a minimal spanning set. That makes them a vector, a basis. And as a result now, we know that the dimension of our new space is just the number of vectors V. And so now we're going to end our proof by saying, what is the dimension of our image? It's n minus m. So for example, the indices from m plus 1 to n. Similarly, what was the dimension of our kernel? Well, we said that that was m. And so if I add them together, I get n. Okay, so I just came back up to the top here, and I substituted in the dimension of that, and I got back to n over there. Proved. That's the entire proof of rank nullity theorem. So the whole point of this is to say that for any dimension size of my kernel, what's the behavior of my image? Is my image still a basis of the new space? If that's true, I can determine its dimension and then just prove that they're equal. All right? So for the second bit here, all we're trying to do is show that my vectors in my new space, right? Because here I start with a vector in my original space and I map out and I'm left with what the spanning set is in the new space, right? Now I want to show that the vectors, these vectors in the new space are linearly independent. I don't want to assume that because the V's were linearly independent in the original space, that now the phi's of V's are going to be linearly independent in my new space. That would have been an assumption. We can't say that. So we need to prove that that's true. We need to prove that if these V's were linearly independent or orthogonal to each other in the first setting, that they're now going to stay orthogonal after the mapping. That's all we're doing here. Okay? So what I'm going to say is, well, let's just take one of them. Let's take any vector in the span of my new space and say, well, is it going to be equal to 0? Okay? Are they linearly independent? You just then use the linearity of your matrix multiplication to pull it out. And it says, well, if that's going to be true, then if I picked a vector in my original space, I would then have to have a non-trivial vector here getting mapped to 0 in my new space, which is the definition of my kernel. In other words, think about it this way. In other words, the only way to keep it consistent would be to be at the intersection of my image and my kernel, okay? Be at the intersection of what is preserved and what is forgotten, which is my 0 vector. The only element that is in every single vector space is 0. That's what this is all just saying here. Sorry, I'm going to try to close this door once more. Yes, what's up?
When you take the image of 5 and it's positive 5, is it because all the K1 up to Km are vectors in the table?
Yes. So we know they get mapped to 0 by 5. Exactly.
At the end of the proof, where you have the dimensions of the image of 5, you have it as n minus n from m plus 1 to n, and the kernel of 5 the kernel of 5 is equal to n.
Yeah.
Where did those like n minus m and m values come from?
Yeah, so that's a good question. So I've told you that the kernel is just the set of ki vectors, right? And there are m of them.
Yeah.
So that's where m comes from for the kernel dimension. Okay. And in that case, we're working in our original vector space. So I already know that the k's are linearly independent of each other. They're a basis by definition there. What we can't assume is that once we map into a new space that we still have linearly independent vectors. I mean, with an understanding of linear algebra, of course, you would think that. But this is like the proof that showed that in like 1600 or whatever. The absolute wizard who kept that door closed. Thank you. So yeah, so that's the whole idea, right? Is you're defining the kernel space, which is m-dimensional by definition. And that's just a definition of my original space. There's no manipulation to be done. So we take that for granted. All that's left then is to try and understand what the new space is, right? And so the new space then is just going to say, well, number one, it's spanned by my vectors that I get mapped onto. It's spanned by mapping my earlier basis, will give me a new set of vectors that I can use to reach any point in my new space. And then I want to just prove that those vectors are also a basis in the new space after they've been mapped, right? Okay, so what I'm trying to say is the basis in my original space that's not forgotten a basis of my new space? And that's all that these two things do, right? I prove that in my new space, those vectors after they've been mapped are spanning, and I've proved that after when they're mapped, they are minimal, and as a result, they're now a basis in the new space too.
We can also say that the dimension of the image of 5 plus the dimensions of the kernel of 5 are equal to the dimensions of the n. That's how we can get that n minus plus n to be back to the original n.
Yes, exactly. Yeah, so all you're doing is coming through and like putting this in, right? Because our theorem is saying, well, what's dim image of phi plus the dimension dimension of my kernel of phi. All right, and I've told you up here, so the dimension of my image is n minus m, right? So it's my m plus 1th index up to my nth index in this set here, right? Okay. Then it's the dimension of my kernel. There's m of them. I told you that, but also it's written up here. So m over there. But I've also said that they are the first m vectors. And so I'm just going to substitute those two numbers in. That's like the end of the proof, is just go put m there, put n minus m there, and then see what happens. And what does that equal? It's n, which is the dimension of my v, for any choice of my original m dimensional kernel. You know what I mean? This m isn't in the final answer. Okay. And so one way for you to check whether or not you're coming to good answers when you're doing systems of linear equations is to check that when you define your general solution, is the dimensionality of your kernel space, how do I say this properly? Is the dimensionality of X plus the dimensionality of your general solution equal to the embedding space that you're in? Right?
That's the image.
The image is what you map onto in your new space, exactly. Yeah.
Why is this so important? Why did I find that?
Okay. So, I mean, this is everything we've been speaking about the last few weeks, right? It's summarized and it's kind of used in this. So what it's saying is that information always has to be accounted for in linear algebra. There's no chance of us applying a linear mapping and having information that either we haven't lost and we know kind of how to characterize what gets lost, or we end up with like a higher dimensional space on the right-hand side. You know what I mean? So we can't, it's almost like in physics, you know, there's the conservation of energy laws. It's the linear algebra equivalent of a conservation of energy law. I can't create information by applying a linear mapping. That's maybe the main key point, is that it restricts the dimensionality of my image. The fact that this is a particular dimension matters, and the fact that it is restricted to be the original space minus the kernel, that might be the more important message, I would say. We good? All right. If there's no questions about this, we can take a break. Cool. I'll see you guys in 15 minutes. Oh, sorry, man. Go back. Yeah. Yeah. Will you just reply to that email saying that it's the link's dead and I'll find another version? Oh, it's the biobank. Yeah. Yeah, so I mean, if you Google the biobank, it'll probably be the first PDF that comes up. But I'll make sure to send it to you. Yeah, it's just a PDF of like a document, like a 2-page document explaining what the biobank is and why it works and stuff like that. I think we'll set up from next week or the week after, probably next week. We'll set up a meeting with Michelle, who's our collaborator with Medical School. We'll start going through the data sets. I'm going to see what you might want to look at. Maybe you want to work at the grip strings one. Like once you see the data set, There's a lot of cool stuff in there. There's a lot of place like space trying to explore different ideas. Yeah. So I think, but I think Michelle will maybe ground our search. No worries, man. Sorry about that. Group theory. Okay, yeah. You need to, you need to prove the first group property as well. You say, you need group closure, associativity, inverse, and an identity element, and then you can prove that it's abelian. The question in the exam will be a lot clearer. It'll say, by defining all five properties or showing all five properties of an abelian group or whatever. And if I'm happy for you to assume that it's already a group, then I'll say, assume this is already a group such that commutativity and all that associativity hold. Please prove only the property of commutativity or something like that. But for that tutorial, you do need to show five.
Yeah.
So when you're doing the change of bases, I noticed that most of the time we're looking at standard bases, right? So mapping from standard bases to non-standard bases.
It's often yes.
But then again, I'm also looking at maybe relating to non-standard bases. So if you've got like one non-standard basis, U and W.
So you obviously, so it doesn't have to be the Euclidean basis, right? It can be something else.
It can be something else. But then when we...
Sorry, I just want to be clear that that's not like a rule we have to.
So then, so if we have two non-standard bases, then how is it different to, I think it was a linear transformation. So that we have something in this form.
Yeah.
So how is something like this? Yeah.
Okay, so don't forget that to me a change of basis and a transformation are two different things.
Yes.
So what you're doing here is you're changing basis there, applying the transformation, changing basis there. So it's kind of like all you're trying to do is find, like I've given you the two vector spaces that this is transforming between. We're trying to find the equivalent in the two different bases for those two different spaces.
So we're changing the basis and also applying the transformation to it.
Exactly.
And then in this case, we're just changing the basis.
Yes, exactly. Yes.
So when we have, I think something like this. So it's kind of got our space here, and then we apply our transformation to the space.
Yes.
So,
yes. It's a trillion order then, right? So it's like how you invert it. Well, you know that they're all your new basis is equal to your forward transform times by your old basis, right? So that gives you a forward transform in that position. But now you know that your transforms are always acting on x. All right, so they're always acting on coordinates. So you're always then going to say, well, to go from old basis, but coordinates in old basis, I use my backwards transform to go to my new basis. So, no, yeah, so let's just draw something. So you got to always separate it out into what's going on in my basis and then what's going on in my coordinates. Right? So in this case, my new basis is the forward transform, the forward transform of my old basis, right? Yeah. Same thing. Back, old basis is equal to, sorry, let's draw it like this. Little v is the basis. It's the forward transform of my old basis. Then the flip is true. I can go from my old basis with the backwards transform to my new basis. That makes sense, right? Yes. By definition, then, they're inverses of each other. If you're working on transformations, they're always in the coordinate space.
So does that mean that the basis will never change, or the cases where we're changing how we represent the vectors and we're changing the basis, or is it just one or the other?
No, you're definitely changing the basis, but a transform goes from one vector space into another. I have to tell you something about it, right? I can't just leave that arbitrary. So what I'm going to do is I'm going to tell you the basis here.
So the new basis.
Well, I don't want to call it old and new because that's what's going on here. But I'm going to tell you the basis for the mapping space, and that's why we have the C's, right? Okay. So that's in the new space. So that also follows the same rules. There's another forward transform, so let's just say B, B. So now I have the forward transform for C space, and I have the backwards transform for C space. All right, and by definition, forward transform for C space is the inverse of the backward transform for C space. No. Okay. You understand what's going on here? All right. So we have these vector spaces. Call it. This is B space. We have this vector space here. This is C space. I am applying a mapping into it. Okay, this is a transformation. It's not, and so this is also why I don't like drawing it in the same dimensions. Maybe let's do this. Let's make it just. I'm telling you that I'm taking data points in here and I'm transforming it to there. So I'm telling you now what the basis that it's being transformed into. I can't expect you to pick all that. Like, I need to tell you something about your new space that we're working on, right? And I tell you that what that is, I tell you that what that transformation is this matrix A.
Okay.
Right. So what you're given at the start of this problem, right? At the start of the problem, you are given, let's ring it, A, B, B inverse, C, C inverse. Okay. And I say to you, well, A maps from B to C. Okay. What is the equivalent transforms? This is the question. What is the equivalent transform of A, which maps from B tilde to C tilde? Okay. So there's two different representations of the same space.
Yeah.
Same space B, same space C. I can represent them both with different bases. I can transform from B to C, and I've told you exactly how that would happen. But what's the equivalent way that it would happen in my new basis? That's what I'm asking you to do. So what you're going to then start with is say, well, I'm in coordinate space, right? Yeah. So when I'm working with coordinates, when I'm working with coordinates, I know the mappings are backwards. Okay. In a coordinate space, if I want to go from a, let's say, X, I want to go from an X with respect to basis B, I must use to X with respect to basis B tilde, I must use my backwards transform. Okay? If I want to go from, and that's old to new. So again, when we're working in the bases themselves, it's old to new, uses the forward transform. Okay? When I'm working at coordinates, it goes backwards, right? Because remember we made that example. If I go from working in kilometers to meters, my unit of measurement, my basis gets 1,000 times smaller. My coordinate must get 1,000 times longer. 1 kilometer, 1,000 kilometers, 1,000 meters. Okay, so it's the backwards transform there. Same here. I can get xb equal to the forward transform of b times by x tilde, xb tilde. All right. Lastly, we can write up the c's. So I'm just going to do that quickly. So x in terms of c tilde is equal to the backward transform for c tilde times by x in terms of c is equal to the forward transform for c times by c tilde. Okay. So these are the only equations you really need to remember, and there are a lot. Obviously, it's like going backwards and forward for my basis, going backward and forward for my transform. But do it systematically. You know, like the reason it takes me long is because I always have to start this way. I always have to say, well, I'm in my new basis, I'm in my old basis, I want to get to my new basis, that's the forward transform. Then I come back here and I say, but if I'm in a coordinate in my old basis, I want to get a coordinate in my new basis, that's the opposite. That's the backwards transform. And you go through the dance. But then what you know is that ultimately when you want to answer that question of what's the equivalent transform, you know that you're going to be doing, I'm going to raise this, right? You know that you're going to be going from B tilde, you're going to need to go to B, you're going to then go use B to go to C, and use C to go to C tilde. And that will answer my question, because when I string those operations along, I would have figured out how to go from B tilde to C tilde. Follow that loop. Okay, now what's this? So we're always working coordinates. So going from a new basis to an old basis in coordinates, the basis itself uses backwards transform. So this will use my forward transform. Okay. Then I have my A matrix. I tell you this. I can't expect you to do it like this is arbitrary. Okay. A is given. It's going to be defined by your problem, or whatever. But for general solving these things, A is given. All right. Now I want to go for C from old basis to new basis. That would usually use the forward transform from the bases, but I'm in coordinates, so I'm going to use the backwards transform for C. And then all you do is you come here and you say, okay, well, there's my backward transform for C. I know how to calculate that. Here's my forward transform for B. I know how to calculate that. I'm given A, and I'm just going to go now. A tilde is equal to FB A B C X.
So does that mean a change of basis is essentially a linear transformation, or there's just
no? It is definitely thought of as a linear transformation.
Yeah.
I just don't like teaching it that way, because then it gets muddy of like, well, why has A been given but B can be calculated? I think I want it to be clear that a transform is something that can actually change your problem. It re-represents, or it kind of manipulates your data, whereas a change of basis is conserved. So it is a transform. You can think of it as I'm mapping from 2D to 2D, and it's a change of my data such that that's consistent. But then it just gets messy. So like, why is that transform consistent and others aren't? And so if B and C were the same dimension, you could think of this as just being 3 change of bases.
Okay. So in this like example, so we're doing a transformation and a basis change, basically.
If you want to think about it, and that's what eigen decomposition is, right?
Yeah.
All eigen decomposition is saying I'm going to take a mapping, some transformation from R2 to R2 or whatever, and I'm going to decompose it into 3 different change of bases: a rotation change of basis, a scale change of basis, and an opposite rotation change of basis. That's all eigen decomposition is like, I care about 3. I like having one complicated change of basis represented as 3 simple ones. That's all it's doing. Singular value decomposition is when it changes my my magnitude. But we'll get there. That's what, 3 weeks time, 2 weeks time. Does this make sense? We good?
Question.
Yeah.
If I had said FB, A, and then BC, does that go to go from B to C? What should be like?
Well, I mean, you just can't go from B tilde to C tilde. That's what you need to solve, right?
Yeah, I mean, like, I have this already, like,
Okay.
how you wrote it here.
Yeah, you need to always go right to left. Yeah.
Then I have a question with the task, the second question.
Yes.
Since it was 1 month, for example, when we prove associativity,
Yeah.
this part here we break it down to A and B. Do we need to prove associativity or do we assume it? This is 1 month.
Well, usually it's going to be 2 marks, like the statements and the solve. But I think how you done it looks fine to me.
So we can just break it down.
Yeah, exactly. I mean, that looks perfect.
Just one more question before I go.
Yeah.
So in both of these cases, would the transformation matrix be consistent, or do you have maybe different?
No, it's doing the exact same thing. Yes. Alrighty, should we get started again? Guys online? Wait, is there anyone on? Hey, we've got someone on. Are we good online? We all happy? Hey, cool. All right. Okay, so today now we're going to start with analytic geometry. This part of the lecture is now pretty definitions heavy. We're going to go back. We've done all along like the conceptual heavy lifting of what on earth vectors are doing, and we're now just going to go back to defining things, and we'll get more of the geometric intuition for analytic geometry next week. But I think hopefully from what you guys will find is that given the fact that we've waxed absolute lyrical about bases and kernels and null spaces and all that, a lot of these ideas are a little bit more hopefully easier to come to grips with. They're all built on those fundamentals. Even when we get to like metric space and stuff, you define that in terms of a basis and everything. So I hope from now that the conceptual heavy lifting that I feel a lot of you are probably feeling, because I know I'm feeling it or I'm trying to explain it, that's going to slightly loosen for a while now, because I think we have hopefully a very good geometric understanding of what's going on. If not, please do slow me down and we will catch it all up. So we're going to explain what is an affine subspace. This is really simple. It's a vector space that's also been shifted. So there's our shift. Okay. In other words, what it is let U be a vector subspace by the usual definition of a subspace. And then we have some other vector that is in V, right? In the same size as the embedding space that we're in. So again, U is a subspace. It might be sitting in 3D, but it might be just a 2D plane kind of cutting through the room. Whereas this shift must be a vector that is actually the dimension of the room, okay? And so what's going to happen is we're going to define a 2D plane relative to the room. So it's kind of like cutting this way relative to the corner of the room. And we're going to then just pull it out, okay? So instead of it being intersecting at 0, which for whatever reason I've defined as the corner of the room there, it's now starting somewhere slightly shifted off. And that shift is happening in the kind of ambient space, okay? I'm taking my plane and I'm moving it around in the ambient space that it's sitting in the embedding space, okay? And so it is just then every vector that's an element of my embedding space that can be decomposed into a vector from my original space, from my U subspace, plus that one shift vector, okay? So as much as now it's a vector that is sitting in 3D, it's still very simply, you still don't have free reign over this V vector space, right? All you have is the same degrees of freedom from U and then a fixed constant shift value. So it's not lambda times x0. This isn't a basis vector, okay? It's a constant shift in one direction away from 0, all right? I'll see a picture of it now. And so in U is called the direction or the direction space, and x0 is called the support points. It is not necessarily a vector space, primarily because it's not guaranteed that 0 is an element of the space. And there's a little proof of this on the side here. But the intuition is that, so I know that I've shifted my vector space off of 0, but if that x0 element itself is not in U, then I can't get the 0 vector out of my affine space. Okay, so what that means is if I have a 2D plane and it's like relative to my hand, right? And it's obviously it starts being tangent to 0 at the bottom of the room. I have now shifted it this way. I can't get back to 0 by moving along U. That shift that I just applied to my hand isn't an element of the plane that it creates. If my hand was like that, and now I can move that direction along my hand's plane, and I get back to 0, then x naught, well, negative x naught, is in the basis or in the set of u. Then that is still a vector space, and in fact, you'll notice that you've just done nothing. Okay, I had a plane that cut through 0, and I shifted it all the way this way, and I still have a plane that cut through 0. But in reality, all that's happened now is it's kind of my 0 point is just being re-represented somewhere else. Okay, but that is then still a vector space because I can still construct the 0 vector, or I can still have the 0 vector and construct any other vector in that plane from it. All right. So an affine space is often discussed in terms of a frame in a computer. So we made that example last week where a lot of these transformations get used in graphics, particularly because the character in a game often defines the basis and the world is in the coordinate space. So if my character rotates to the right, okay, the transformation changes in the opposite way from my coordinates. It's as if my world moved to the left. Those are equivalent transformations. And it's the same kind of thing, except now affine space is how the character moves forward and backwards in the world. Okay? Your character's view window is starting here in front of me. If I walk up to the stairs, that plane is going to move forward. All right? So affine subspaces are often represented as a parametric equation. So if we let L be that kind of space, so a vector space plus a shift, the k-dimensional affine space where B is an ordered basis of U, then every element in that space can be uniquely described as a linear combination of my basis for my original space plus the support point added back to it. Okay? Again, I'm taking a vector space, I start with a vector space, subspace, and then I just shift it around a little bit. Okay, so in a 1D example of an affine space, they are called lines, and it can be written as follows. So we have our basis vector B1 times by some lambda elements of the reals, okay, and that represents moving along that basis vector there. All right, so that defines a vector subspace. You can see that it's slightly tilted, so the ambient space here is R2, okay, but the line itself is just real numbered. Okay, we only have lambda that we can set freely. So that's an R, lambda element of R over there. But I now apply that shift, and that shift can happen in any direction. So even though my basis is pointing off there, I can still shift it along the purple vector up to the left. Okay, and now that is my affine space. But you'll notice that it's still a line, right? Again, I can't now arbitrarily move along the purple. I can only say I started here, I moved to the purple. I started here, I moved by the purple. Start there, move by the purple, and I just get the same line with the same basis vector, but just shifted off. Okay? So we're not gaining a degree of freedom by having a fixed x naught. Okay. This idea can be directly extended in R to n-1 dimensional affine spaces, and these are called hyperplanes. And what you'll notice is that when you do something like linear regression, if you include a bias variable, that's a fixed constant shift that you're applying. That is the same as defining an affine space. If you're just doing linear regression by saying pretty much that, where you have I don't like x here. So when you do linear regression, you'll probably have x times weights is equal to y. Okay. If you do linear regression like this, then that is defining a vector space where, let me not write that like a deck. X w is equal to y, or let's go theta. Theta. Right, so that's our matrix. Okay, you usually have some data set that's n by m. Then you'll have your n-dimensional vector or whatever, and that gives you your n by 1 regression outputs, right, for n data points. Okay, if you solve that system of linear equations, that's doing linear regression. But if you now include a bias variable, so b plus that, so let's not go, bias variable, ignore this notation for now. Then now you're saying, we'll take this vector space that I'm going to learn and shift it off. And you can see the benefit of that if you have data lying along this line. Okay? The alternative would have been to try and use two basis vectors to do that same job of representing a line, right? You could try and now learn your parameters such that you're actually restricting yourself to having an actual basis vector there and a basis vector there. And so those are the two parameters of your, regression, right? Your regression is constraining your degrees of freedom, and the basis you're using, and it's called kernel methods. When you think of your data as defining a basis for a linear regression, then your parameters are being constrained to match the data from that basis. Okay, that's what solving that linear equations is. But then a bias variable is useful because maybe I don't want that degree of freedom off of that line. If my data looks like this, then that degree of freedom is just another source of error. That's just another way that I'm going to make mistakes. Maybe I'm going to stick my learned hyperplane much off of that. Now it's like that maybe. Who knows? So that's why we always include, not always, that's why in a lot of regression tasks, the benefit of having a bias is that it takes away one degree of freedom in terms of basis and replaces it with some kind of really restricted but useful fixed shift. Okay, so affine space, linear regression with a bias term, vector space, just straight up linear regression. Alrighty, that's somewhat of a detour for this class, but maybe trying to ground it in some prior knowledge. Okay, for our purposes, let's get back to mappings and vectors. So consider the system AX is equal to B, right, where A is an n by n matrix, X is n dimensional, and B is m dimensional. The solution of the system is either the empty set or an affine subspace of Rn of dimension n minus rank of A. Right? You can see the kernel nullity theorem in there. Okay, it's what information remains. Right? But the reason that it is an affine subspace is because this B acts as if it is your support point. This is your shift off of the axis 0. Okay, so that's what we're doing there. Okay, everyone following? Great. Affine mappings, then, it's the thing that you can extrapolate pretty easily from vector mappings. It's just a mapping on an affine space. So you have your same phi we've been speaking about today. That maps the vector space the same way as usual. So you have a linear mapping on your vector spaces, V and W. And now you also have A, such that you also add A to the mapping afterwards. Okay, so this is an affine mapping from V to W. The vector A is called the translation of the affine mapping of a vector. Okay, so it's not just doing matrix multiplication anymore. I can take an element of X, do a matrix multiplication, and then shift it as well. Right? Many of the useful properties of linear mappings are still preserved in affine mappings. So, for example, you can compose them. And so if you have an affine mapping from V to W and then from W to X, you can get an affine mapping from V to X. Affine mappings keep geometric structure invariant. So things like geometric structure or lines that are parallel will stay parallel. Angles will be preserved. Okay, and they keep the dimension the same. All right. An affine mapping can also be constructed from composing a linear mapping with a translation. So that's kind of obvious. That's somewhat by definition. But what's nice is that then you can break down all of the translations into one set of composition and all of the matrix multiplications in another. Right? So essentially, and I'm not going to do this fully, but let's say you start with X and you're doing an affine mapping on X. What you're going to do is you're going to matrix multiply it plus B. And then if I wanted to do a second affine mapping, I would do another matrix multiplication plus another shift. But if you solve all of this, what you would get is BAX plus BB plus C. And you can see that this is now murky because what we're doing is matrix multiplying our previous shift. And that's necessary. But you can always decompose this into just the shift and just the matrix multiplication. All right? There's an equivalent representation. And so that's sometimes just useful for clarity and so on. What's up, bro?
Going back to the analytic, what is X? That's like,
What's X?
X is 2.
Sorry, I'm not confident about the
X
question.
is an element of V.
Oh, yeah, X is elements of V, yes. All right. So again, we're taking some elements of V and applying a transformation to it, which takes an element of V and maps it to W. Okay, and then after we've done that mapping, after we've applied phi, it now is in W space, but we can then apply another shift to it after we've done that mapping, and that shift is also coming from the dimensions of W. Is that all right? Okay. Cool. And so that's affine spaces, and so that ends all of linear algebra that we're going to chat about. Well, I suppose, you know, by this book's definition of linear algebra. We're now going to move on to analytical geometry, and that's where we start speaking about things like how do we measure distances, how do we know that angles are orthogonal, what does it mean to be a rotation, those sorts of ideas, but it's more in line with, I guess, building up towards, I guess, geometric ideas of linear algebra, at least the geometric applications of linear algebra. Not so much keeping it abstract in terms of bases and null spaces and all of that sort of thing. So the first important definition we have is that of a norm. So a norm of a vector space V is some function that takes in an element of that vector space and maps it onto a real number. Okay? So you can usually denote it like that. I put the 2 here because that's the Euclidean norm, but there are others. And so this assigns for each vector x its length, right? And this is the notion of how long the line is along the ground, such that for all lambda elements of the reals and all xy elements of V, the following holds. Okay, so this, for it something to be a norm, you have to have these 3 properties over here. The first is called absolute homogeneity. So if I'm calculating the norm of a vector times by some scalar lambda, that is the same as calculating the norm of the vector itself, multiplying by the absolute value of the scalar. Okay. I'm not going to ask you to prove something's a norm, so you don't have to memorize these ones. For most of those definitioning things, I can't say for certain, but it's usually going to be the group theory stuff is where we do the proofs of equivalence or whatever. Not proofs of equivalence, but proofs that something's a group. Okay, so then the second property is a triangle inequality. So if I take 2 vectors, add them together, and then calculate the norm, it must be less than if I calculate the norms separately. And it's the norm inequality because, sorry, it's the triangle inequality because if you imagine it, it forms this triangle. Okay, so if I take my vector x and apply it there, and I then take the length of y separately, the dimension of those 2 things separately must be less than the hypotenuse off the top of it. All right. You can also draw it the other way where you put y on top, like that, and then you get your length of vector v there. I just drew them both from the same origin point there. Okay, so it forms a triangle, and it says that going directly x, y, z. It says that going directly from x to z is quicker than going from x and then y. So applying the vector z is quicker than applying first x and then y, at least. Okay, that's a triangle inequality. And then lastly, we have the positive definiteness case. Your norm must always be greater than or equal to 0. So there's no such thing as a negative length, all right, of a vector. And if the norm is 0, then that means that the vector itself had to be the 0 vector. So we don't want to be taking a vector that's sitting in 2, 1 and saying that it has no length. Okay, the only time when a vector has no length is when it's sitting at the origin of our vector space itself. Right. So the first example of a norm is known as your Manhattan distance. And all you do there is you take your vector in Rn, you sum up the absolute value of all of those elements. Okay. It is also called the L1 norm. Okay. And if you are doing machine learning and you apply L1 regression, or L1 regularization, what you're doing is applying minimizing the absolute value of the weights of your neural network. Okay. Secondly, if you then, the L2 norm is known as the Euclidean norm, and this is one probably most of you familiar with from like Pythagoras in school. In this case, what you do is you square all the elements of your vector, you add all those squares up, and then after that, you square root it. Okay? It corresponds to applying this operation here, which we're going to get to in a second. which is known as the dot product. But essentially, it's just the same as saying I take all of the elements of my vector independently, square it, and sum it up. Okay, this computes the Euclidean distance of x from the origin. It's called the L2 norm. There is a general definition of these things. That is it. So it's called the P norm, and you can see that it fits the definition of L1 and L2 if I set P equal to 1. Okay, if I set P equal to 1, what I get is x1 is equal to the sum of the absolute value of xi. Okay, if it's 2, then it's obviously the same thing. I guess that's power of this xi squared raised to 1 over 2. 1 over 2 is square root. But it goes into general and arbitrary, magnitudes. Okay, that then leads us to an important point. And again, for this week, I'm going to stick to a lot of just definitions for this. I will give you some geometric intuition for what an inner product is doing next week. There is fortunately something fairly geometrically kind of clear about it. But for now, let's just stick to the algebra. So the example of an inner product you have likely encountered is the dot product. Okay, so that's in this case where if I have two vectors x, t, and y, okay, then all I'm going to do is I'm going to take the first elements of my vector on the left, multiply it with the first elements of my vector on the right, and then sum that up with those products of all the matching elements. Okay, so it's the ith element of x times the ith element of y, and then you sum that all up. Okay, that gives you a scalar. All right, is anyone unsure about this? And I'm going to probably go quickly through this, but we're all comfy with this, right? We've been doing matrix multiplication, so it's a little bit ridiculous to do this now, but we're good? Okay. There are general inner products then, and this is getting a little bit more important, the fact that you can define more interesting ways of measuring distance on a space. So in order to provide a compact definition of a general inner product, a couple of preliminary concepts are needed. The first is bilinearity. So we covered the concept of linearity, right? It's when you can FOIL something. So if I have some operation phi, and it's acting on alpha A plus beta B or something like that, I could then always distribute it and pull out my scalars and then distribute the sum as well, plus beta phi B, right? So the scalar always comes outside of my operation, and then I can also just apply it to the sums individually and then add up at the end. This is the exact same thing, except now it's when I have two arguments to an operation. Two arguments, because as you will see, most of these things require 1, 2 vectors to make a lot of sense. Okay, but importantly now, they are still linear with respect to both arguments individually. Okay, and the last important thing there is that if I'm applying the linearity to my first vector, then I just keep the second one the same. Okay, z isn't changing, but I am distributing this in for the first argument, such that my lambda is now sitting outside of my omega, my phi is sitting outside of my omega, and in the x and y arguments are now being applied linearly, right? Same exact definition, we just have the lingering z there. Same story when I apply this to my second argument. I keep x the same, and then I just apply the linearity arguments to the second, the linearity conditions to the second argument. Okay. Equation 12 asserts that omega is linear in the first argument, and equation 13 asserts that it is linear in the second argument. I've drawn at the bottom there the slower steps of this. So first we apply the fact that you can separate summation, and then secondly we now pull out the lambdas and the phi's out front, and you get back to your full conditions there. So that's just a reminder of each step being applied separately. Okay, then we have the notion, so that's bilinearity. Then we have symmetry and positive definiteness. So let V be a vector space, and we have some bilinear mapping. Again, we have two arguments that are both vectors, okay, mapping onto R. So they are now going to be bilinear mappings. Then omega is called symmetric if I can swap the order of my two arguments. This isn't going to be generally true for most mappings, but if I can, then that mapping is symmetric. Okay. What you would notice is that we've called a matrix symmetric before, and the definition of that was that A is equal to AT. If I can transpose a matrix, then it is symmetric. And we know that matrices form mappings. It's how we perform, well, linear mappings in linear algebra. All of these operations can be represented by matrices. And so what you'll realize is ultimately this means that it's kind of looking for whether or not we have a symmetric matrix. Okay? Then omega is called positive definite if for any x in our original space, excluding 0, if I use that x as both arguments into the function. So it's not if I'm saying xy. Xy is possible for an inner product, but if I'm now saying x twice being passed into the inner product, that must now be greater than 0, and only if that x is the 0 vector itself is it allowed to produce the 0 vector, the 0 scalar. Okay, so don't get that confused, right? It has to be both arguments being x. Okay, then we get the inner product and inner product spaces. So let V be a vector space with a bilinear mapping, omega. Then a positive definite symmetric bilinear mapping, so all three of the properties we just spoke about, is called an inner product. It's often denoted as that. Okay, the pair of a vector space plus this operation is called an inner product space. So oftentimes in notation, you just put these little dots as like placeholders for, you know, x, y, or whatever there. Okay, if we use the dot product defined in equation 11, so let's go have a look at that. If we're using this as our inner product, okay, so a dot product is one type of inner product, okay? If we're using the dot product as our inner product, then what we get is Euclidean vector space. Okay. Let's see if, yeah, now's the time. There are a number of inner products in Rn that are not the dot products. So for example, you can define it as follows. So if I have, I've defined this inner product for xy, and I'm saying I take the first argument of each of them, the second argument of each of them, multiply that second argument by 2, and then have this cross product part of it, then you can also show that this is an inner product, right? It will still map onto R. It will still be symmetric, such that if I passed in y, x, I could rewrite that as being the same as xy. All right, I can apply the linearity to both of them. So if I passed in alpha x plus beta y comma z here, that would be the same as then foiling it out and applying the linear property. And the way you would do this is you would come and take this property into there, right? And say, well, x1 now is alpha x1 plus beta y1, okay, times by z1. And so this glob over here, call it star, replaces that x1 element there, because that's what my first argument is, okay? And then all you would do is, you know, FOIL this out and show that it works the same way as if I did alpha, what's it, alpha inner product x and all that. Mark it right, I think you guys get the gist. Okay, there's also tutorials on this. Okay, so symmetric positive definite matrices in the related theory provide vital formulations for convex optimization and by extension many aspects of machine learning. The last chapter of this class is on continuous optimization, and so we'll kind of come to see how it gets used. But mainly the whole point is that in machine learning, what we care about is distances. The most common one is how the distance that we are on. How far are we away from what the data says? I need some kind of inner product or a way to measure that. Okay, and so there exists a direct relationship between an inner product on a finite dimensional vector space and a matrix operation. Specifically, if we let V be an n-dimensional vector space with the inner product defined generally there. So it's going to be taking two vectors from our vector space and mapping onto the real numbers. And there is an ordered basis B. Then if we take this inner product xy, right, we have two vectors that can be written as a linear combination of our basis vectors. Two different linear combinations. So there's phi and there's lambda, two different variables. That is by definition x and y. We can apply, again, the linearity of this inner product and pull out the scalars from the inner product itself. And what we're left with is the fact that this is going to then be a summation over the multiplication of our basis vectors weighted by the two scalars. Okay? This will then give us something that is then as if it is where these are the coordinate vectors of x and y. Okay? So the AI over here becomes a matrix, which is the inner product of all the I elements of my basis with all the other elements of my basis set. Okay? And then what we're left with then is just the x, which were the coordinates in terms of those bases. So what this means is that for any change of basis or any basis on a vector space, I can define a metric that acts just on its coordinates. Okay? And if I change the basis, the way I measure distance on that space will change. Okay? I will get a different A, and that'll be a new metric. So this matrix is called a metric. Does anyone want to maybe hazard a guess? What would happen here if our basis vector, if these basis vectors were completely orthogonal in unit length? So they're basis vectors, they're orthogonal. But what do you think is going to happen here? You're going to end up with A being the identity matrix, because this will only be 1 if it's BI, BI, which is your diagonal. Okay, I is the diagonal of this matrix, and then 0 otherwise. What that then ends up being, if you continue this line of reasoning, is just this equation here. You sum up over all your indices, xi, yi of your coordinates. And you end up getting back to Euclidean space. So Euclidean space corresponds to when you're working within a basis that is orthogonal, okay? Or you actually, you're trying to define your vectors in terms of these orthogonal bases to each other, and so you can now interact with your variables in isolation. You can treat the system as if it is a set of one-dimensional problems rather than this like highly coupled system, okay? Because don't forget, the BIs, these will not necessarily be the same basis. I think maybe the slides aren't super clear on this. They don't always have to be the same representation of space. They can be different basis vectors, and so they're not always going to be necessarily be not overlapping. So you can get an A that is more complicated, has off-diagonal couplings, and so on. Okay? But if you can write your system in a set of linear equations such that this A matrix is the identity, then you can treat all these elements separately in Euclidean space. Okay, so what can we show now directly say about A? So A is symmetric if BI and BJ is the same as BJ and BI. And we have that for all x in the vector space excluding 0. If I apply the, again, x matching twice to it using that metric, that A, it must be greater than 0. Because we know that the inner product itself is positive definite. Okay, we know for a fact that this thing up here is positive definite by definition, and so that carries over down to the bottom there. Okay, we'll come to a lot of the intuition for these things next week. We just need to get the big formal statements down. So symmetric matrix that satisfies equation 19. In other words, it is symmetric positive definite. If we do not have the strict inequality and we only have a weak inequality in equation 19, then we say that the matrix is symmetric positive semi-definite. And in that case, that corresponds to if you have a low rank set of vectors here. Okay, you're going to get some 0 elements in A, such that when I apply that mapping there, you don't occupy the full ambient space. So now you can get a 0 vector. You can end up mapping that original x coordinate onto a 0, and then now you end up with 0 times A times 0. Okay, so if the equality doesn't, if it's not strict and you can say greater than or equal, then it's positive semi-definite. And so for a real valued finite dimensional vector space V and an ordered basis B of V, it holds that that this mapping is an inner product if and only if there exists a symmetric positive definite matrix defined such that that is your inner product. Okay, so only if we can represent the mapping itself as a vector, as a matrix that is symmetric and satisfies this property, will we be able to call then that an inner product. So two further properties of a symmetric positive definite matrix: the null space or the kernel of A consists only of 0. Okay, if, and again that's positive definite. Okay, this can be seen by noting that since Ax greater than 0 for all x not equal to 0, then this item here cannot get mapped to 0. Or it can only get mapped to 0 if the x element itself is 0. Okay, so A cannot have a null space such that any x gets mapped to 0. Okay, and then lastly, the diagonal elements of A, call it AII, are all going to be positive, because what you're taking in the middle there is that, you know, your base is I, base is I. Cool, so the diagonal elements are positive, and so observe that if we use the canonical basis, so EI, the ith vector of the standard basis in Rn, then we see that, oh, my bad. Then you see that this is the same as just saying, well, I'm going to take the canonical basis multiplied by I, so that will extract that diagonal element from it. Okay, so what we've done here is we have a matrix A, B, C, D. Then you go 1, 0, 1, 0. This, if you FOIL this out, gives you A. Okay, it's a way of returning your diagonal. All right, looks like we're at 4 o'clock. I think let's take a 15-minute break then we'll come back and wrap up these slides. We only have about 15 left.
Yeah. Some people are looking, I don't know. No, you just guide there. You underline what the nonsense is. You underline and you say. Because I wish you were there to see the people, right? Wait. Oh, Michael failed. Oh, Michael failed. I think I find one saying and the rest are 0. That's what I'm saying. Like, my people are saying that people are like 5. I'm hungry. I want to go to my room. I You know what I did in my exam? My the product
So we will always say it's a game format, I will do CV solution. So that was also mainly one of the first areas. So the main idea is that like, you want to be able to feed in like a PDF and extract context from it. So put a vision from it. And also then you want to be able to translate like those little, when you find a little letter or something in the document, that corresponds to like a visual token. Then you're doing token, visual tokens, language token. You want to go to regex, so it's like really usable token. So it's regex as its own like language, so to speak, as a form of evidence. Exactly. So that's just you know like language, one language, word of letter tokens to like for things to sequence. So yeah, so I think Steve's been doing the project for the constitutions collaboration. Yeah. So I think you know, as far as motivating the project, I think that's really good. So you interested in the project, you doesn't have someone on there, maybe you can and see if you, I would recommend you get engaged. I think I was looking at that OCR one because the technology of the machine vision is like established, and then on top of that, like sequence modeling is also like we can't know how to transform it. But I thought it would be cool to get about like machine MLOps, like how do you deploy like a machine product kind of research. Because I think there's interesting work in that direction. It's something yeah.
Even play like a more app,
Have machine learning models. Yeah.
whatever sort of text that you provide.
Yeah, so I think that was mainly more than what I was going with it, but I think you're gonna be creating like a pipeline for that problem, and then you might as well work on the constitution, and then you help reduce some impact. Yeah, so I think switching topics is hard once you're allocated. You know, because now it's a case of whatever you were allocated to, students and taking students from that person. So you need at least the other supervisor to agree. You need Steve to agree. Yeah, if you want to be the ML ops idea, if you want to do it, you're welcome to take that. You know, I'm not precious about that idea either. Oh, did you not get the first option? Yeah. There's like my one for students. I probably allocated some students. Like I can get anyone on that. But at the same time, just because then once I find out about students, I try to get that from students. So I'll reach out to Steve. Yeah, thanks for the interest in my project. I'm sorry you didn't get it. You know the basis.
So this one.
So these are compounded.
Yeah.
No, wait, my outro. So now we
All right, guys, should we jump back in? All right, I just want to, I think I misspoke there at the end, so just want to clear something up. I said that these were two different bases. That's obviously not. They're two different vectors in the same basis. Okay. The reason you might get like off diagonal stuff like that is if I'm in 2D space, that's still a basis of R2, right? Those two vectors. But they can be, you know, if that's BI and BJ is those two things, then their inner product is going to be non-zero, right? They're not orthogonal to each other. That's how come you might get an A with off diagonal elements. And then similarly, there's no guarantee that your basis vector is unit length, right? Like it might be very long, might be very short, can have different lengths. and so the diagonal itself also might not be 1, right? So in a case where we have orthogonal, let's say like that, those two basis vectors are now orthogonal, so anytime you multiply them together, you're going to get 0 unless I is equal to j. And then lastly, they, by definition, let's say they have unit length, then bi bj will be equal to 1. Okay, that's only in the special case of your basis vectors being 90 degrees to each other and having unit length. Okay, so I'm sorry about that if that was confusing the way I explained that. I hope that clarifies it up a little bit. And the last thing just to say is that these x and y hats that we get here, when we package those together, well, when we package the phi I together, we get the x hat. When we package the lambda j's together, we get the y hat. Okay, so that's just stacking those i's and j's into their corresponding vectors. So I know it's a bit of a frustrating kind of notation, but it is then y I is equal to lambda 0 down to lambda n, or whatever. Yeah, n. Okay, same for x. It's your phi's. Okay, is that comfortable? I hope I don't confuse anyone the way I explained that. We good? Okay. Okay, then all the other stuff still holds. Obviously, you need your positive definites definition, unless the vector x itself, the coordinate that you're working with, is 0. Okay, so then we're going to get through the last few definitions. So one of the reasons why I like kind of stopping there in the slides is just because I think it can get a little bit murky, the difference between dot products, inner product, and a norm. So a dot product is a kind of inner product. It's when it has that Euclidean metric. Okay, and so that means that there is now the orthogonal unit length basis vectors. Okay, that's when A gives us that identity matrix like we just spoke about. That gives us Euclidean metric. But there are others that would be the same as having a dot product. But there are other inner products, as we just saw, with the different kinds of A's. But whenever I take an inner product and then square root it, I get a norm. So we've already discussed different norms, but there's a special class of norms that are induced by inner products, specifically of that form. All inner products induce a norm just by square rooting them, but not all norms are induced by an inner product. A norm is induced from an inner product if it follows this parallelogram inequality. Okay, so if I apply the norm to x and y separately, square it, and then multiply it by 2, it must be the same as adding them together, calculating the norm, and then taking the difference of them, calculating the norm, squaring it, and then adding that together. So it's just a weird kind of constraint on it. I'm not going to go too much into why that holds or derive it or anything. That's just when, if you have an inner product that when you define a norm, it follows this. Well, if you use an inner product to define a norm, it must follow the parallelogram inequality. Okay. One of the more important ones is the Cauchy-Schwarz inequality. So in an inner product vector space, so remember an inner product space says that I have a vector space and some inner product that takes two elements from that same space, maps it to R. That was my mistake earlier. It has to be elements from the same space working with the same basis vectors. Maps it to R and induces a norm. So for an inner product vector space, with that inner product, the induced norm satisfies the Cauchy-Schwarz inequality, which again says that either I can calculate the norm of x multiplied by the norm of y, or I can calculate the inner product of x and y and absolute value it. And so one thing just again to note is that for the norm, it has to always be x and x or both arguments to it, while the inner product in general can take x and y's. Okay? Just be careful when you're speaking about the norm, it's always the same vector as both arguments to your inner product. The inner product is this general thing with A. If your A is an identity matrix, you get back to the dot product. Okay. Then we can define a metric, and a metric is what we use to describe distances. So we've already kind of seen this. If it's starting to feel old hat, I know it's kind of subtle definitions that don't always even apply super well linear algebra. But if x is a set, so again, we're going super general now, not just vectors. if X is a set, then any mapping which takes two elements of that set and maps it to a real number. Okay, so for example, X and Y getting mapped onto this D function. It is a metric and it's called a distance if it satisfies the following properties. So if this function that is applied by D is positive definite, okay, and oh, you good? So D is positive definite such that it is greater than or equal to 0, so in that case positive semi-definite. Okay, and if the distance is 0, it implies they're the same vector. Okay, that's the first property. D must be symmetric, so whether I go X or Y or X must give me the same answer, the same distance. And then it must have a triangle inequality. So if I compute the distance of X and Y and the distance of Y and Z, then it must be less than doing the distance of X and Z directly. Okay, then we will have what is known as a metric. We do not need to be this general in this course and restrict ourselves to X as vector space as opposed to an arbitrary set. Those are three definitions. And again, in our case, the distance metric in our case is when I subtract two vectors, gives me a new vector Z, and then I calculate the norm on Z. In other words, I will then come and square root inner product and use Z as my inner product twice. Okay, that is a distance metric between X and Y. Okay, so that's our fourth concept. Do not forget in a test to do that, please. That is a big mistake people make. I know that in a test it's very easy to do that. Certainly I've done that before, but it's just like, one of those like frustrating mistakes you make because you can see that you understand what's going on, but you just didn't remember to subtract them. So please, when you need to calculate distance, remember, subtract first. Gives you a new vector Z. Then come along and do the norm of Z, which is then the square root of the inner product of Z, okay, which is then something along this line. And I know the next question is, will I give you A? Yes, I will give you A. All right, so it's going to define, I will tell you what the metric, that's often called a metric tensor, but I'll define that matrix there in the middle. A.
X minus Y only Z, or is it for normal Z as well? Like the X minus Y, does that evaluate to Z or to normal Z?
So I'm just defining a new vector, which is X, Y, subtracted Y, right? So like, I have two vectors in the space. I have vector X, I have vector Y. I'm going to subtract them, which then gives me that vector there, right, between those 2 points. I'm just calling it Z for convenience. If you guys want to, if you feel comfortable, you can then just jump along. So define you go straight to the norm calculation, in which case it's square root of X minus Y, X minus Y. Okay, if V is an inner product space, we can go a step further, and then you always use the induced norm, which is just exactly what we just did. Cool. Again, keep in mind the difference between a distance, a norm, an inner product, and the dot product. What's up?
So, no, I just need a learn. So, can you say that every inner product space can be reduced to norm, and every norm space can be reduced to a vector space?
No, that only goes one way, right? So all inner products induce a norm.
Norm and norm.
Yes. Yeah, exactly. So we can, if we have an inner product defined, we can use that to define, I don't know if it's called a norm space, but we can use it to define a norm on the space, which means that we can then calculate distance on that space. Okay? It's not true that every norm has a corresponding inner product. And I'll show you an example at the end. There's like other ones with like integrals and stuff. But for the case of particularly finite dimensional linear algebra, you're going to always then just have an inner product with that A matrix, which then can be used to induce a norm, which then if you go X minus Y is used to induce a distance. Is that fine for you? Okay. All right. Cool. I'm going to say it once more. Distance is the subtraction of the two vectors. Then you apply the norm. The norm is then just the square root of xy. Xx. I made that mistake. Xx. That comes from an inner product. Okay, but the inner product itself can be general, which is then xy for arbitrary things. And then if this inner product xy is x times the identity matrix times y transposed, then that is a dot product. Okay, so again, keep the difference between distance, norm, inner product, and dot product in your minds. Okay, but you can see why we care, right? Because ultimately, like I was saying, in machine learning and all these things, what we really care about is defining distance. That's like how wrong are we? How far away was I from being correct? That comes from having a distance metric. And so to have that, you needed a norm. And to have the norm, you needed the inner product. And to have the inner product, you need to like define your basis and all that. Okay, so the inner products capture the geometry of a vector space by defining the angle omega between two vectors. So observe that we can obtain the following directly from the Cauchy-Schwarz inequality, and I've drawn that up here. Okay, so from the Cauchy-Schwarz inequality, we know that the norm of x times the norm of y will be less than or equal to, change color as well, will be less than or equal to, first doing the inner product between x and y, and then taking the absolute value of it. Okay, if I divide both sides by the norm of x, norm of y, okay, this bit here, what I will get to then is this term here. Okay, not super neat, but essentially it's just that this absolute value of the inner product in x and y divided by the norm of x divided by the norm of y must be less than or equal to 1, right? Because on this side I just divided by itself. If I drop the absolute values at the top here, this means that then I have greater than or less than equal to 1 and minus 1 on either side. Okay, so the minus 1 appears here because I'm getting rid of the absolute values at the top. So I just need to account for both sides of that magnitude. And so this is then how we can use this to define angles on the vector space. I'll show you the kind of geometric interpretation of this next week. That's kind of how we start next week's lecture. So that's a little bit fuzzy of like where the cos comes from and all that. It's because we have to map into polar coordinates first to actually derive this. So take it a little bit for granted now at the moment, but you can check that it's kind of nice that when these things are orthogonal, you will at least get 0, and you can check that these fall a certain range of what you would expect from cos, from the cos function. Okay, we know that cos is bounded by -1 and 1. So at the very least, this is starting to make sense. Okay, furthermore, there exists a unique angle in radians, okay, such that cos of the angle is then equal to that inner product divided by the two norms. One thing I like kind of thinking about, especially if you're trying to make sense of why this might work, and again, we'll go through this again next week, is if we know that this is a scalar, right, and that's a scalar, by the definition of a norm, we know that inner products are linear operators, right? And in fact, we know that they're bilinear. And so what that means is that I can suck that scalar into the top there, and that scalar into the top there. And what I end up with is the inner product of x divided by its norm, y divided by its norm. Okay? This here is how you normalize a vector. We'll speak about it again later, but normalizing a vector means that this new vector x hat, call it, has unit length 1. So if I go norm of x hat, it's 1. Okay, what that corresponds to is obviously going the norm of x by the norm of x. And we'll at some point prove that this gives you 1. All right? For the moment, why I like thinking about this is you can see then that we've normalized the vectors in this inner product at the top here, right? And so obviously the only thing that's going to now be able to even be measured in terms of the distance is not magnitude, because I've just extracted magnitude. I've just normalized that away. And so the only way that x and y are going to differ now is by pointing in opposite or different directions, which is why this is now going to give us a representation of that rotation away from each other, regardless of how long the two vectors are. Because regardless of how long they are, I'm going to normalize them anyway to be unit length before I then calculate the difference. That's at least some intuition. Again, next week we'll do the polar coordinates version of this, but that's at least some intuition for why this equation is geometrically giving me angle, because I've made it independent of the length of the vector. All right, and then yeah, please remember to put your calculators into radians for this. That is also a good way to get frustrated. Okay, so then that allows us to define what is now known as orthogonality. And I've been speaking about this up to now, but let's define it properly. I'm sure you guys all kind of know what it is already. But two vectors, x and y, are orthogonal if and only if their inner product evaluates to 0, right? They are denoted by that little symbol there. I don't know what it's called. But if, in addition to the orthogonality, we have that the norm of x and the norm of y is 1, we say that x and y are orthonormal to each other. Okay, a direct implication of this definition is that the 0 vector is orthogonal to every vector in the vector space, because obviously if I say x 0 in a product, it's going to give me 0. Okay. All right, but orthogonality means that these vectors, in accordance to this inner product, are pointing in different directions. An important thing I want to point out here. This is an inner product, right? Which means that it follows this pattern here, x transpose A, y. It is, the vectors themselves must be orthogonal when considering A. Or in other words, when considering those basis vectors. That be, when they're multiplied together, construct A. Okay? So it is not always going to be true that, you know, these two vectors are not orthogonal to each other. You can't visually inspect x and y, say, well, they're not 90 degrees visually, and say they're orthogonal. It depends entirely on your basis. It depends entirely on this A matrix that comes up. And so in tests and in exams, because there's a procedure that we do called, to get an orthonormal basis, it's called the Gram-Schmidt method. When we do the Gram-Schmidt method, I'm going to tell you the metric A. I'm going to say you're doing it in terms of that. So whenever you then see a norm or an inner product in those things, you always have to be consistent in terms of the inner product definition you're using. You always use the same A matrix, okay? I have been complaining or kind of saying this for a couple of years now, and the trend I found is that what people will get to is they will come to this calculation, and what they'll do is x transposed A y square root x transpose x y transpose y. That is wrong, because the A should be in there and the A should be in there too. Okay? You always have to be consistent with the metric you're using to define your space. Metric being that A matrix. So don't do that. Wrong. Before that becomes unclear. Cool. Okay, so we can get the orthogonality over different inner products. It is worth noting the originality of two vectors depends on the inner product orthogonality. Orthogonality of two vectors depends on the inner product used. So for example, if we have x and y defined as follows, then we can use the dot product as the inner product. Dot product meaning axy is equal to x identity matrix y, which is the same as x transpose y, which is then just the sum xi yi over I. All right, so those are all equivalent. Okay, so if we use the dot product as the inner product just for this example, then we have that we can calculate over there. So we're taking x1 and 1, so that's -1, and then 1 times 1, that's 1. Adding them together, we get 0, And so in that case, they are now orthogonal, or pi over 2 radians. Do you guys know what a radian is? Yeah, what's up, Nick?
That's what you just said we shouldn't do.
Yeah.
We're saying that when we expand the norm, we should put the A there. Right?
Yes.
Yeah, why we for the norm, the A is an identity matrix.
If you're using the dot product, the A is the identity matrix.
So for the norm.
Yes?
Yes. The A is an identity matrix for the norm.
Yes.
And then for the inner product, there has to be an A.
No. So you induce a norm from any inner product. Not any inner, yeah. Any inner product can induce a norm. It doesn't have to be the identity one. You just have to be consistent. Okay. Well, I'll speak through radians next week. Actually, I think that fits in with that Pythagoras argument. For anyone who hasn't, I assume that's high school stuff, but I assume it might be a good refresher. Okay, so you can then do the exact same problem with this inner product here, and then you'll come out to a different solution. And I'll leave it to you guys to go and calculate that out. Okay, it's a good example. Maybe just checking over here that things work out as you expect when you use both the inner product in every way, right? Okay, orthogonal matrices. So a square matrix, it has to be square, is an orthogonal matrix if and only if its columns are orthogonal. So as a result, when you multiply A times A transposed or A transposed A, you get the identity matrix. Okay? And this implies also that when you have an orthogonal matrix, its transpose is its own inverse. Okay? So in other words, when I take, feels like this is missing one slide. Yeah, I don't know where this one slide is. I think let's move on to this and then we'll loop back around to that. So transformations by orthogonal matrices are special because the length of the vector x is preserved when A is applied. So for example, in the case of the dot product here, if you have a transformation A, so I've been using A for the metric. In this case, dot product, the metric is the identity. Don't get confused with this being A. Notation is hard. But this is a transformation of X, right? So it's a transformation of a vector space. If I'm transforming X and then calculating a norm, again, the norm here is now the Euclidean norm. That is the same as saying AX transposed by AX. This is an identity. AX all transposed is the same as reversing the order and then transposing separately. Okay, so what happens is now we get A transpose A in the middle. Okay, so in this case now, if all the columns of this matrix are orthogonal to each other and they are unit length, then that is what's called an orthogonal matrix. Okay, and so we will get back out to the identity. All right, that's why we like having this property of orthogonal matrices, because it says that every column of my matrix must be 90 degrees, or depending on your metric, it must give you 0 when it's inner producted with any of the others. So AI with AJ gives you 0, and then when it's AI, it must give you 1. Okay? Such that in particular, this version holds. Then what we get to is an identity matrix here, and then we're left with just the dot product of X in its own right. And so what you can see is that orthogonal matrices, when I get the norm of a vector that has been transformed by an orthogonal matrix, then it will have the same norm as the original vector itself. Okay, it doesn't. Orthogonal matrices, when they represent transformations, do not change the length of vectors. They do not stretch any vectors. Okay, additionally, the angle between two vectors is also preserved when A is applied, and we can do the exact same thing, right? So again, using the dot product, you can substitute in AX and AY to see whether or not it changes the equation by having the A's in there. you calculate out the A transpose in the middle, that gives you identity. Same for the norm over here. That will then just be the same as what we just did there. Okay, so we're applying this identity on this slide to get that and that and that and that to just be separate. Okay, same rule. At the top, you get the identity matrix. And we end up at the equation for the angle between two vectors as if we're treating the vectors separately and not after they have been manipulated by an orthogonal matrix. And so orthogonal matrices preserve the angle between two vectors. Okay, this A mapping might rotate, right? So it still might change kind of the space, but it will not change the relative angle between two vectors. And so we have previously used bases to perform a number of algebraic tasks. A further refinement of the concept is, however, useful, namely an orthonormal basis. So consider an n-dimensional vector space V and a basis B1 through Bn of V. Then if any vector is orthogonal to the other, or any base vector is orthogonal to the other, and it's when the indices match, they give you 1, then this is known as an orthonormal basis. Okay, same ideas. We've defined orthonormal vectors, but now we're talking about a basis, a minimal spanning set of a vector space. When that minimal spanning set has orthonormal vectors, then it's an orthonormal basis. People call it an OND. Okay, if only equation 32 is satisfied, then the basis is called an orthogonal basis. So it's not normal in the sense that its basis vectors are not unit length. We can extend the idea of orthogonality then to entire vector spaces, and this is kind of what I was talking about earlier with the rank nullity theorem, right? We had a vector space that we could map onto, and then we had another vector space that was forgotten about, and that had to give us the entire original vector space. Same thing, those two vector spaces are orthogonal to each other. We use that property in the proof of the rank nullity theorem, right? And so we can consider a d-dimensional vector space V and an m-dimensional subspace, then use orthogonal m-dimensional subspace U, then use orthogonal complements is just the remaining dimensions of D, right? So it's a D minus m-dimensional subspace of V. So essentially you can think of it as I have a 2D vector space like that, and then again, I'm never the best artist, but let's see if I can get it right. Okay, you have another space intersecting it at 90 degrees. Then those can be orthogonal subspaces to each other. And so if I picked a vector in the green subspace and I calculate its inner product with any vector in that red subspace, it will be 0. Okay, the entire vector subspaces are now orthogonal. You can then also represent any x as a weighted sum of basis vectors from U. And so you first note that the intersection of two bases is 0. So that 3D picture I drew there wasn't quite correct because they intersected at a line, right? You would really want them to be both two-dimensional, intersecting at just 0, but I can't draw that. Okay, and then so you can then decompose this 4-dimensional vector, let's say, into one 2D basis and the other 2D basis of the vector subspace of itself, and then its orthogonal complement. And that'll get you back to a vector in the original subspace. In other words, you can decompose the vector into the basis defining its kernel and the basis that's used to define its image. That was the rank nullity theorem in a nutshell. Okay, but ultimately, if you have orthonormal bases, you can then just split the summation out, or you cannot, and then just you just merge those two summations. But there are occasions where it's useful to split out an orthogonal subspace. Okay. And just one point of notation terminology, we tend to not speak about matrices as being orthonormal, even though they might be. So when we say that it's an orthogonal matrix, it's when the identity matrix we multiply it together. It's a bit of a frustrating thing. Often when I speak about it in class going forward, I will call it an orthonormal matrix. That is technically wrong. I just like saying that so it's clear. Because what this does imply, just by saying orthogonal matrix, is that the columns of A are also unit length. Okay? So it is a little bit more, when I say an orthogonal matrix, it's implying the normality of the columns, which I don't like that being implied. That's just one thing I want to mention. And then obviously when we stack those columns into a basis, we will then often maybe going forward talk about the matrix constructed from your basis, and that will be an orthogonal matrix, which means it's an orthonormal basis. Okay, just keep that in your mind. I'll bring it up again, and then sometimes I will try to say an orthonormal matrix, but that's incorrect. And if you go speak to a mathematician about it and you say an orthonormal matrix, they will scoff at you. Okay, last thing for today, and you're welcome to zone out on these last two slides, but it's worth mentioning. Up until now, we only really consider the inner product of finite dimensional vector spaces, which again, that's what this course cares about, but it is possible to extend this concept more broadly. Specifically, you can generalize it to other entities such as countably infinite entries. So countably infinite is like the integers. There's an infinite number of them, but you know that there's no space between like 1 and 2. So in theory, you can count 1, 2, 3, 4. That's a countably infinite set. And there are also cases where you can calculate it on uncountably infinite sets, such as the real numbers. And so one example of this is through an inner, is through this integral. So if you have two functions defined on the same like support or domain x, then you can just apply both functions u and v and integrate across x. And that will give you something of a similarity metric between those two continuous functions. The same way we think of matrix multiplication performing a mapping, which is a function. You can do this with more general functions like this u and v on a real domain. And then you can now define an inner product for functions. This is then how you get into things like real analysis and the notion of functionals and stuff like that. So there's a bit more nuance with regards to precisely defining an integral for these concepts and how you then get into things called Hilbert spaces. But this is just an extension of linear algebra into the ideas of continuous, these kind of continuous functions and stuff like that. We, however, can use this perspective just for practical cases because I'm not going to ask you about this. We care about linear algebra. It's worth knowing that that exists, and that's like the next maybe step of that. All right, if there's no questions and we're all happy with the definitions we brought up in the last like hour and a half, we can call it there. Is everyone comfortable with these definitions? There's nothing, because we have 10 minutes here to make sure we're solid. We're good. That's fine. Is it in the course outline that it's next week? Then we're writing next week. No. I'll do it tonight. Let me put that in my calendar right now. It's based just on what we did up to last week. So just the first chapter. Up to and affine vector spaces as well, like that stuff up until the linear algebra finished this or earlier today. What's up, man?
Is it possible to post the two?
Yeah, I'll do my best to put it up. I mean, so for today, this morning, I was writing the rank nullity theorem proof, which is why it took a bit longer. But I will try in future to put out quicker. No worries. Give me 2 minutes to talk this out.